For this Lab 4 regarding oscillation, we were asked to observe and plot the motion of a mass oscillating in both the x and y direction on a spring. We also were asked to use the momentum and energy principles to create a computational model through GlowScript to model the same observed motion. Through this computational model, the kinetic and potential energy of the spring and mass, as well as the potential energy due to gravity, was able to be observed and analyzed. The momentum principle, as well as Newton's second law, was essential in the creation and understanding of the computational model and called for the use of the equation change in momentum equals force times change in time. Additionally, in regards to the forces acting on the system, the net force is equal to the spring force and the gravitational force, which can be rewritten as F net equals Ks plus mg. The energy principle was utilized in this lab too, and the knowledge that there is no work that was being done on the system means there is no energy change, so delta E equals 0 newtons. Delta E can also be written as the sum of the change in kinetic energy of the mass, which has the equation K equals 1/2 times mass times velocity squared, change in potential energy of the spring being 1/2 times the spring constant times the displacement of the spring squared, and the change in gravitational potential energy being the mass of the ball times the gravitational constant of 9.8 times the displacement of the mass in the y direction. To find the values such as the spring constant, initial position, initial velocity, and period of oscillation that are used in these equations, I used the observed model and the application tracker. This allowed for the tracking of the position of the mass on the spring as well as shown in the video. The data collected regarding the x and y position information was compiled into a graph of position versus time through tracker and was moved to a CSV file for later use. This allowed for us to find the initial position, which was at the coordinate -0.126, -0.613, 0 meters, and the initial velocity was 0 meters per second. Additionally, the given mass is 0.402 kilograms. From the graphs provided, the period of oscillation was found by dividing the time it took for the mass to complete 3 oscillations in the y direction and dividing this value by 3, resulting in a measurement of 1.52 seconds. These values allowed for the spring constant to be measured using the equation stating that the period of oscillation is equal to 2 pi times the square root of mass divided by the spring constant. Rearranging this equation and plugging in values for t, the spring constant was found to be 6.869 newtons per meter. The relaxed length of the spring was also found by using the equation that the force of gravity is equal to the force of the spring. This can be rewritten using the non-relaxed length of 0.7 meters and the spring constant to solve for the relaxed length, which was 0.126 meters. Now that we have sufficient values to create a computational model in GlowScript, the values for mass, initial position, initial velocity, spring constant, and relaxed spring length were inserted into the program. Following this, the correct equation was inputted for the length of the spring to be used in later formulas. The formulas discussed earlier for kinetic energy, gravitational potential energy, and spring potential energy, as well as total energy, were inputted as well. Finally, a while loop was created that updates the velocity of the ball using Newton's second law and the position of the ball using kinematic equations of motion. The values for kinetic, potential, and total energies were also calculated, as well as the change in these values. The energy changes and the x and y position of the mass calculated are plotted on separate graphs to be seen in the execution of the model. In running this program, the CSV file storing the observed data is inputted. The model shows the motion of the simulated ball, which is in blue, as well as the observed ball, which is in red. This model creates a graph modeling the different energies of the system calculated in the while loop of the program, as well as the x and y position versus time graph, where the model is in blue and the observed is in red. In the position versus time graphs, there is a difference among the modeled and observed data. In both the x and y position graphs, the model overpredicts the motion of the mass attached to the spring. This is because the force of drag was not taken into consideration in the way it impacted the observed system. However, as stated in the discussion of the physics principles needed in this lab, the energy principle allowed for us to predict that the total energy would be equal to 0. The total energy in the program was said to be equal to the sum of gravitational and spring potential energy as well as the spring kinetic energy. This value was 0 in the computational model shown, displayed by the orange line. There was a difference in the period for the x and y position versus time graphs. Both were calculated in the same way using 3 periods of oscillation, but when using x, the period was 1.615 seconds, and when using y, it was 1.52 seconds. I chose to use the y computed period since the spring is in the y direction. However, the difference in these values would cause a large difference in the computational model, as it would change the value determining the spring constant and the relaxed spring length.